Welcome back. Let's continue. Where was I? I was explaining to you how complicated it is, more than it seems, to actually construct an index, and especially the pre-processing. So what I was saying is that we need to infer the encoding of the documents. Sometimes there are ways, of course, you can read with the first bits or with metadata of the file and so on, but not always. It's not trivial, right? So you need to come up with a way, because otherwise what you are going to decode is going to be gibberish. So this is why. So maybe it's user-defined and you know it from other sources. Maybe it's annotated. Maybe machine learning is also, who knows, a way of decoding the documents. It might also be software specific. Maybe it's none of these. Maybe it's encoded in a way that's specific to the some proprietary or open standard, right? So that's another way. There are other encodings, for example, escaping characters in XML and so on. This is an ampersand, this is a lower than sign and so on. So, you know, you basically need a lot of work in order to figure out all that. Do not underestimate XML. It's very popular, for example, with digital humanists who index plenty of old articles in order to process them in the information retrieval way. They have a lot of XML in there. So they use XML very heavily. So this is why this is important. It can be binary also in some formats. Another aspect is the language. You know, you need to figure out, is it English, is it Spanish, is it Chinese, and so on and so on, right? So that's also a way that machine learning can help you with, right? The encoding, the language, the type of document, and so on. So you see, not easy at all. There is a bit of work to be done there in order to even start. And we'll see the language, the importance of the language. Another challenge is, what is the granularity of your documents? Because, for example, imagine this is an enormous email archive, but you have 10,000 emails in there. Maybe you want to be fine-grained. Maybe the document should be one email. Each email is one document. In that case, you need to separate that enormous file into smaller files, and each one gives you a document, right? So in one case. In the other case, it's the opposite. Maybe what you're looking at in some LaTeX paper or LaTeX book that is spread over multiple files. Maybe there is one file for each chapter. So in that case, it's multiple files that you need to group as a single document, right? So this also is something you need to figure out. What is the document? What is the document? Where is the boundary of a document? That's also something that is important, because that affects the quality of the search results if you're too small or too big in what a document is. All right. Okay. Another aspect of building an inverted index is the tokenizing. How do you create the terms? So we suppose now we solve the rest. We know what a document is, we know the encoding, we know the language, and so on and so on. So the very first thing that you're tempted to do probably is to throw away the punctuation. There you go, the point, the comma, all of that. Let's throw it away, right? It's tempting to do that. Not so fast. It's actually not so simple. And here are a few. It's just to challenge you, to make sure it's not so trivial. What about apostrophes in English? Isn't it, right? You cannot just throw that away. It's not two words. It is not here. What about commas, apostrophes in names? What about dashes in English that are here in order to group words together? What about the dots that indicate abbreviations like versus? Oh, sorry, yeah, that's one, but sorry, I just got carried away. So this is one indeed. But here, I think the point I wanted to make is the spaces, website in one word or website in several words, right? What about, for example, the names of proper names like cantons in Switzerland, Basel-Stadt? That is one term, it's one canton. You don't have Basel and Stadt, it's Basel-Stadt, right? So the arrow base in an email also, you cannot throw away the dot, right? So it is not easy at all. And I have plenty more examples in there to show you that it's even worse than it seems. Here's one that is difficult. Los Angeles-based company. If you just look at spaces, you're going to have Los Angeles-based and company. That doesn't make any sense. Of course, you want Los Angeles and then based and then company, right? But you see, it's not trivial at all. How can you tell just looking at punctuation, right? Here you have San Francisco - Los Angeles, right, for the flights, but this is how you need to tokenize it, right? San Francisco and Los Angeles. So you see, not easy at all. York University versus New York University, right? Maybe you think, okay, that's York University and you didn't see the new in front, right? So you see that these are all examples that are found that were, the credits go to this professor, but basically this is very, very complex and much more complex than it seems at first sight, right? numbers are also a corner case, because how do you parse dates, for example? Is it the American way or is it the European way, right? Month first or day first, right? Maybe you have dates encoded in a semi-English way, right? Mark for March. Maybe you have dashes that give a room number, for example, at ETH, an IP address, here a phone number. You see, do you use dots? Do you use parentheses and so on? So this is also not trivial at all. Now, there are aspects to consider. Now let's dive into languages. There are aspects to consider that has to do with the language that you use. Because I'm teaching in English. English has the luxury of having a very simple conjugation in the use of the words, right? So for example, if you conjugate like this a verb, I would like a coffee, you would like a coffee, you would like a coffee, it's always the same, right? Because when you conjugate, especially with an auxiliary verb, you don't even have an S here. So it looks like this is trivial to index. You just say that the term is would and you're done, right? This is with English. The problem is that even with English, you know that the third person already causes problems, because then you need to consider the S that is in there, and you still probably want to index it in the same way. Right? You want to say once or want. It doesn't matter. If somebody searches for once, they should also find once. And if somebody searches for once, they should also find once, right? So it's not trivial. But of course, in other languages, it's even more complicated than that. But there are also, let's start with the easy ones. There are languages even simpler than English. Can you imagine that? Swedish is even simpler than English. Why? Because there is not even an S in the third person. Jag skulle vilja ha en kaffe, du skulle vilja ha en kaffe, I would like a coffee. It means it's the same in all persons. Swedish is basically the easiest of all in terms of conjugation. Do we have any Swedish people in the room, by the way? From Sweden, or who speak Swedish?
Yeah, we have someone here.
We have someone, wonderful. It's a beautiful language. I like the sound of it. And also there is a bit of German in the words that you find, but it has the simplicity of English, and the order of the words reminds me of French somehow. So it's kind of a nice mixture of these three languages. All right. But I hope you agree that the conjugation is super easy in Swedish, but there are complicated stuff. Like I know that, for example, this is supposed to be pronounced dom and not de. And of course, this you need to learn by heart if you need to pronounce it. All right. German. So here I assume that almost everybody in the room actually speaks German. So here you will understand what I'm telling you, right? In German, it's exactly the opposite. Here, I don't think there are two persons that are the same, or maybe wir, sie, maybe. Ich möchte einen Kaffee, du möchtest einen Kaffee, and so on. So here you see these changes every time. And this is when we are lucky, because you know that for some verbs, we even change in the middle, right? Ich fahre, du fährst, you even have to have a change in the middle of the word, right? So you can see the difficulty. Indexing German is going to be more complicated than indexing English for this reason, because you need to take that into consideration, right? In German, there's another problem. So here I'm basically showing all the challenges. We're going to have plenty of languages today. Another challenge in German is that we like to paste words together. So this is, I think, the officially longest word, at least when I check in the Guinness World Book of Records. It reads Donau dann Schifffahrtselektrizitäten Hauptbetriebswerk unter Beamtengesellschaft. So it means the society of blah 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 of the steamboats of the Donau, right? But the thing is, if it were English, you would have spaces everywhere. It would all be separated, but not so in German. And probably you don't want to index that as a single word, but you want to index Donau, then Dampf, Schiff, Fahrt, Elektrizität, Haupt, Betrieb, Zwerg or Betriebswerk, Bau, Unterbeamten, Gesellschaft. So you see, you need to basically cut it. This is also part of the pre-processing when you need to do in there. Then comes Swiss German. Don't get me started on that. It's an awesome language. I also love it, but it's more complex also than it seems, because it's not exactly like German. So it has a lot that resembles it, but so in that example, you had Denk, du hegen Kaffee welle trinken. That's already one difference, is that you need to swap the words, right? Ich habe gedacht, du hättest einen Kaffee trinken wollen, but in Swiss German, you say welle trinken. So you have to do a lot of gymnastics in order to reorganize things a little bit. There are a few tenses that disappear in Swiss German. You don't have the preteritum and so on. You use, as you see here, the past perfect instead. What else is there is Swiss German that is interesting. So this is, yeah, I think that's the main one. There is another one that when you say also the zu, zum Beispiel, machen zu wollen, will es machen. You also swap the two when there is a zu in the middle. So, and the difficulty, of course, of Swiss German is also that technically it's not a written language. It's supposed to be a spoken language. Of course, it was, when I arrived in Switzerland, it was still true that it wasn't really written. Nowadays, everybody writes Swiss German. So there are spellings that people can use. The problem is that there are as many spellings as persons. And you can imagine the challenge of actually parsing Swiss German just because people do not use exactly the same spelling for the same language, right? And this is because it's real life, right? This is how people use languages. And when you do information retrieval, you just need to index real world data. Let's look at another one, Chinese. Do we have people who know Chinese in the room?
No.
Nobody? All right. So I'm assuming not many people understand that. I actually cannot read really Chinese either, but I was told by previous cohorts of students that this was taken from Wikipedia. This actually merges two sorts of characters because there's the ones that are simplified, probably these, and the ones that are fancy, that have more more lines when they are written, and that actually mixes the two, and that's the first challenge: the fact that you have several versions of the symbols. You can see in the middle there are some Indo-Arabic numerals in the middle, 2 and 3. In that case, what is also specific to that language is that you need to learn. It's not like in English where you have 26 characters. In Chinese, you have thousands of these symbols, and you need to learn as many of them as possible. I don't actually know if anybody knows all of them. Maybe it's not even possible. So you need to learn many symbols. So of course, when you parse that, you are going to do it symbol by symbol, probably when you parse, right? All right. Another particularity of Chinese, but this is when it's spoken, is that you have the sounds that go like ah, 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 ah. So it goes up, down. There is the flat one, the down and up one, and so on. So this is also a nice feature of the language. Okay. क्या इस मामले में कोई हिंदी बोलता या बोलती है? Do we have Hindi speakers? Nobody? All right. This is also a great language. So this is called the Devanagari script. It's a different one. It's actually not like Chinese in the sense that these are actual letters, just like English or German, just like the Latin alphabet. For example, this is an M, this is E, this is I, S, T, M, that's for the R. This is A, for example, but this is actually the A is displayed because it's at the beginning of a word, but in the middle of a word, it wouldn't appear. For example, here, there is an implicit A between the T and the M, right? So it's easier to parse in that sense because it resembles the Latin alphabet, but there are a few technicalities in there. So here, this sentence, so me isterm acha par rahahun, it means I am studying well this semester. What you notice here is first, when you conjugate the verb, if it's a male or a female speaker, that changes the conjugation. It's not the case in German or in English, right? When you say ich möchte, you don't know if you're male or female. But in Hindi, you do. Raha is male, rahi is female. So the R or E actually changes it, right? Then even in the present, you have an auxiliary hun that means I am. So that's the I am studying. And you see here that tells you the first person. So this resembles a bit German in the sense that ich möchte, that's the first person, du möchtest, that's the second person. So that tells you the person, and that tells you the gender of the person. Like in German, there are cases, but it's not like nominative, accusative, dative, genitive. In that case, there's just two of them mainly. There's a normal case in the oblique case that is for all the rest. So for example, is term, that means this semester, it's like dieses Semester, right? So you don't see the difference in German. Dieses Semester studiere ich gut, right? But in Hindi here, you just need to change the case, and that tells you that this is actually an indication in that case of time. And like in German, that would be ich, that would be mir, muche. So that's that also exists. That's actually also an oblique case. But what they do in Hindi is that they have this case, but they then add a preposition after it. So this is why you only have the oblique case for everything, and it's the preposition that follows. That makes it challenging to parse, but actually easier than German for this reason, because you can split it according to the preposition. All right. So by the way, this is the first person, Hun. This is the third person, He. All right. And the future, if you conjugate, you see how it changes here. So the future is actually a suffix. This doesn't exist in German. The future, you say ich werde kommen, but in other languages like in French, je viendrai, you actually add a suffix. In Hindi, it's also the same. If you say I will study, parhunga, so it's also that suddenly you add a suffix to the verb. And here too, in the future, you see that it's a male because uga and ugi, ungi, that's a female speaker. All right, but enough about Hindi. It's also a beautiful language. There is another language that I also find very interesting. It's the Siberian Yupik. Does anybody speak Siberian Yupik? Okay, I think there are not many people on Earth that actually speak it. So it took me a lot of time to actually manage to find a sentence in that language. But you will understand why I'm telling you, why I'm giving you this language as an example. This is probably the hardest one to parse ever if you want to index a language. I'm going to translate that for you. So this is the reference if you're interested. So nek means to eat. Yaktuk means go to. Yuk means to want. Uma means the past. Yag means some frustration. You're frustrated, right? Pet means that it's inferential. So it turns out that something happens. This here is the third person, and this is also Lu. So now you can reassemble the pieces of the puzzle, but the thing that is scary in there is that this is actually an entire sentence that is just fitting in one word. So it's not just like German that we paste words together. Here is the entire sentence that we compact in a single word. So it means actually, if I translate that, also it turns out that she or he wanted to go eat its butt. All right, so you can imagine the difficulty of parsing this language. All right, I'm done with languages. Why did I do that? I wanted to show you that the diversity of languages that we have on this planet makes it very challenging to create information retrieval systems, because you need to consider the specificities of every language that you use. And especially when you want to group words together, when you want to look at cases, conjugation, and so on, it basically makes it challenging. So you would not implement the system in the same way for English, for example, as you would do for German or for French. And I will also give you a sense of the sort of techniques that are used for one language that might not be suitable for another language. All right. So now that we know, given these languages, that some of the words might be grouped together even they do not look the same thing, let's give you some terminology. First, assume we have tokenized. So we managed to put together the pieces. So now I put these little rectangles around the words. What each one of these rectangles is a token. It's a token. A token is what you get right after the tokenization. You haven't built the index yet. It's just the pieces of text. It looks like I'm disappearing here, some light effect. So again, okay. So you have a piece of text that's called a token. Then you have what we call a type, but it's not a type like in a programming language. A type is several tokens that are the same, in the sense that in the standard inverted index, they will be the same term. They will be the same entry, right? So we merge them. So we have hour and hour, we have com, but also, and this is coming back to what I told you about languages, is and be would also be together. It's the verb to be. And of course, in English, it's going to be easier, but as you saw in a language like German, French, Spanish, Hindi, and so on, that's going to be much more complicated than that to figure it out. So type is the word for that. You can see it as an equivalence class. You can see it as an equivalence class, and this is what's going to become one term in the standard inverted index. All right. Something else that I want to tell you about, speaking of this be and is the stopwords. Because in many languages, there are some words that appear everywhere, right? So it's, of course, in English, you can speak like kind of, sort of, you know, like you have all these expressions that are verbal expressions. You could consider it that this is what it is. The eigentlich in German is also a very common one, but it's also this is, it. So these are the words that basically have appear at many places. So these ones we tend to ignore, right? So there are lists that have been compiled. For example, that's the Reuters lists. These are the 30 words that are the most common in the English language. And these are the ones, if your resources are limited, when you create your information retrieval system, you want to drop them completely, right? So this is called the stop word, and you don't even bother to index them. What is the trend? Well, that's interesting to know. A long time ago, we had a lot of them. Why? Because we had less computers, less memory, less space to store, and so on. So we had hundreds of stop words back then. The trend today is almost no list at all. If you look at search engines like Google or Bing or Yahoo and so on, they don't even have stop words. They are able to, they index every word. Of course, it's much more elaborate than what we are building in this lecture, the way that they are going to process queries and so on, but they actually do not completely drop the stop words, and there's reasons for that. For example, some of the terms that you might be searching for example, C as a programming language, you know, like there's all these, all the terms might actually have some relevance, and you don't want to ignore them, even though they would be very common. All right, so this is just a general trend in the past years or decades that we had large lists when we didn't have a lot of resources, and nowadays a bit less. We tend to want to keep everything, because we can, actually. That's the main reason. We have the computers, we have the resources. So here are a few more things to consider when you actually build these types and group things together. Also showing to you it's not trivial. So I already hope I convinced you that it's not trivial already because of the way languages work, that there is more to it. So here, for example, you want to group USA, some use dots, some don't. Then you have this 19th century English. If you are indexing like Oscar Wilde or, you know, Sherlock Holmes and so on, these old books, then you will notice that there were a lot of dashes in there. That's because in German, we don't hesitate. We just paste the words together and that's it. In English, it takes decades to happen. You first use the two words together, then you add a dash, and then at some point, the dash disappears. And you have, for example, words like doormat, keyboard, you know, the dash disappeared for them. We just write it in a single word, just like German. And this evolves. So if it's from 2 centuries ago now, then you still have today or tomorrow with a dash in between, but now we no longer write it with the dash. And that also needs to be considered. But it's the same, it's a type that's the same term really. Then you have windows with the uppercase and so on and so on. But of course, now you immediately see that maybe here you mean the operating systems. And here again, it's not trivial because you don't know if you're talking about the actual an actual window that you open and close, or if you're talking about the operating system. Then you have Zurich, and so on, all the ways that this is written. So this would also be grouped together. All right, so what you do typically, since we have these equivalence classes, you know, if you see equivalence classes in math, that it's very common to take a representative of an equivalence class. So you take one of the tokens in that class, that is the default one, and then you rewrite everything replaced with the main representative. For example, you decide that USA is the main one, and whenever you see this written that way, you replace it with this form. Here you can decide that to-day, you notice that it's in that type, but you use this one as the main representative. So you basically replace everything with the main representative of the class, and that's called normalization. You normalize the tokens, and then it's going to be easy to recognize the types, because then you just compare string-wise, right? If it's the same string, then it's the same type. And that's because you did that replacement, all right? So if you just remove characters, that's the easy part. We can come up with rules in order to do that. As I told you, there is the problem of the operating system, that if you have probably written that way, you probably don't want to consider that it's like Windows or window and so on. But if you do have windows, probably you do want to consider with uppercase as well. That would be the beginning of a sentence. This is asymmetric. So it means we cannot do it with an equivalence class. That cannot be solved in this way, right? By grouping together and just putting in the same bag. It doesn't work anymore because this breaches symmetry. So then there is a different technique in order to deal with that. It's called expansion. It works by associating in an asymmetric fashion every token with a list of tokens that are equivalent. Now you can expand in two ways. Either you have this original index that you built in a naive way without considering that, and now you end up with two terms, for example, lift and elevator. These are the terms in Great Britain or in the United Kingdom or the United States, but these are the same thing. So you want to group them together. But if we use expansion and not the types or the equivalence class, what we do instead of putting them together in an early phase, instead we first build without grouping and then we expand. So it means that here I take elevator had 1, 4, 6, and I add the 5 that I took from here. The same goes the other way around. In that case, it happens to be symmetric because I did it both ways, right? But you understand that when you do that, it totally works if it's asymmetric, right? So you can expand the index. So you first build the index without the expansion, and then you post-process the index, and then you add the new postings in order to expand it in that way. That means that when you actually look up lift, you will immediately resolve to these 4, and that means that you consider both lift and elevator in the original document. But there is another way to do that, which is the other way around. Instead of doing it on the index, you can do it on the query. So when somebody says lift, you can rewrite the query as lift or elevator. This is something you probably saw with SQL in the data modeling, the data management and modeling lecture, right? Because you can rewrite a SQL query in an equivalent one that might execute faster. So it's the same sort of thing, right? So we expand the query, but then we keep the original index, right? So we have lift and elevator in that case unchanged, but you see that thanks to the OR, this is how with the union that I showed you just an hour ago, you are going to merge these two lists. All right. Oh, and I have a question for you about expansion. So which statements are correct? Index expansion takes more space, but queries are faster. Index expansion takes less space and queries are faster. Query expansion takes less space, but queries are slower, or query expansion takes less space and queries are faster. Given what I just told you. So we have a majority, and I believe the majority is correct, so I probably don't have much to explain. Indeed, index expansion takes more space because you create a copy of the index that is even bigger, right? But the queries are faster because you don't have to compute the union. And the query expansion takes less space because it's the original index, but the queries are going to be slower because you need to replace with the OR version, and then you need to compute the union, right? All right, so it means you got it. That's really perfect. Let me get back to the slides. All right, I just need to make sure that I'm going to land exactly on the right slides. All right, yeah, that's the one. All right. Oh, no, don't think that's the one. Yeah, let me not take any risk. Then I'll just move forward. Just want to make sure that I don't skip slides because otherwise you'll be missing some of the material. All right, so that we already saw. I'm not sure why somehow the marker for that one wasn't placed properly. So this is where we were. All right, so I showed you, you see, it takes more space and it's faster, and takes less space, but it's slower. All right. All right, so normalization also, just a few examples that I'm dropping at you. There's many more in the book, by the way. If you read the book, you'll have plenty of examples. You can throw away the accents, the umlaut, and so on. That's one way to normalize. You can take the lowercase of everything, then you get rid of the uppercase characters. Then you also have what is called the true casing. That's, I'm not expanding on that, but basically with machine learning, you can, again, that's the same thing with Windows, right? Windows, Apple and Apple, is it the company or is it the actual Apple? So here too, by using a bit of machine learning, which is not part of this lecture, but Andreas Krause's lecture, you can actually also decide when and when not to drop the uppercase. So here you keep the uppercase, here you don't. All right. Now let me talk to you about stemming. So stemming, it's a popular technique. It works in English. It will not work for many other languages, but it works in English. It's the idea of trying to group the words together, this type thing that I told you of putting words together that belong together. It's done by throwing or chopping away the end of the words in some smart way. So basically you transform these words to the stemmed version. That's the one you're going to use. Of course, it's not even English anymore, right? But you don't care because this is really for processing. It's in order to process and build the terms. So here you drop the S, here you drop the E and so on. And basically you're going to have many words that end up with the same stem. So you basically chop the letters of the word. The way it works, the most popular one is the Porter stemmer. It's very popular. It just has a set of rules. It's purely mechanical. You don't even need to understand English in order to do that. And you just follow these rules strictly. And if you follow these rules, it's going to basically transform all of your terms until you run out of rules. And it's going to compute this stem, right? So again, what happens is that every word in the original text is replaced with a stemmed version of the word, and this is what gives you the types. This is what gives you the equivalent classes. Then you can use these as tokens, where if it's equality, basically, that means it's the same term. So this is the Porter stemmer, what it gives you out of this text. This is the Lovin stemmer. It's another one that just does it in a different way, and this is the Pace stemmer. Right? So just so you know that there are several versions of it. The reason it's very popular is that it's incredibly simple to implement. It's just a bunch of rules that you just hard code somewhere, and then you just do it. It's purely mechanical. It will transform that text into that text. And then once you have that, again, you just compare for equality, for string equality, in order to get the terms into your standard inverted index. All right. So stemming works great in English. Because it's a language that somehow has the appropriate structure. But in other languages like German, French, Spanish, and so on, Hindi, it will not work for the reasons that I explained earlier with conjugation. So the idea then is that you need to actually think on a higher level of semantics. It cannot be purely mechanical or syntactic. So this is the actual language when we speak. Then this is the syntax when we analyze the way it's written. Then the higher level is the semantic of the language. It's what you mean. And this is something that is kind of the holy grail of languages. It's some hypothetical universal language with which you can express anything. And basically, the ultimate translator is going to basically translate your language to this interlingua and then translate it back to another language, right? This is really theoretical and hypothetical in that paradigm, but basically you can be at any level. And the idea is that if you're at the stemming level with the Porter stemmer in English, you can do that on that level, syntactic level. But if you do it with other languages, you need to go higher in abstraction. So Limitization, we can also do it in English, of course, means that it's called morphological analysis. It means you realize that these are the words of the same family. Computer, compute, computes, computed, computation, computing, you know that they all belong to the same family. Right. So Limitization means that you recognize that and you put them in the same packets, right? So this is a single type, basically, all these tokens. Again, I insist, it works great in English. It works absolutely great. But I realize I have only 2 flags. I could have added also plenty of other flags like Australian, New Zealand, India, but yeah, it's English that I mean here. Limitization is not helping there. It's really the Porter stemmer that is very popular. But for languages that have morphology, like where you conjugate the verbs, like this is German, French, Spanish, Italian, and so on. I added a little Swiss flag because I think that all the national languages in Switzerland do actually have that, in Hindi as well. So in that case, the Porter stemmer is not going to help you, first because it's designed for English, but also because the technique is not applicable. And then you need to actually understand the conjugation, the cases, the genders, the plural, singular, and so on, and really analyze the language on a higher level in order to make it work. So here, I hope I convince you by now, with all of these challenges that I've thrown at you, it is very, very complex, very, very complex. And what makes it worse is that it even depends on the language. You are not going to build your system in the same way if you are indexing English or German and so on and so on, right? So I'm done with the part on this complexity. Now I'm getting back to a more technical part. Do not be scared if that was a lot, because I wanted to scare you. So if you're scared of what I've shown you, then that's it. That's what I wanted, right? Because if it means you understand that it's complex, that it's challenging, that it's complicated, and that it's not as trivial as I might have made it sound like last week when we just tokenized with the spaces, right? Please read the book, chapter 2. You will see there's even more examples than what I've shown you and more languages in there. So hopefully that gives you this perspective. And now you know, I mean, the Porter stemmer is a must know in information retrieval. It's a classical. Yeah, that's what I wanted to share with you. All right. Do we have any questions so far before I move to the skip list?
It seems like in the room there's no questions.
No questions, and not even Zoom chat either. All right. So now let's move back to this structure. It's purely technical again. Skip list. So let's come back to this, you know, with what we did last week. We had the postings and the standard inverted index and so on that we built. And we had the intersection algorithm that where we walk through the lists in order to compute the intersection. Okay. Let's do it then. Let's take another example and do it here. Okay. So we initialize the pointers. We're at the beginning right there. We compare 1 and 1, intersection, that's the same, so we put it in there. Then we move by 1. It doesn't match, so we take the lower one and copy. What I'm doing here, oh yeah, that's because it's the intersection. So 3 and 3 now match. So I put the 3 in there and I move by 1. Now I'm comparing, it doesn't match, so I increment the lower one. Doesn't match, so increment the lower one. Doesn't match, so increment the lower one. Doesn't match, so I increment the lower one. Doesn't match, so I increment the lower one. It doesn't match, so I increment the lower one. Oh, now it matches. So I copy down the 10. Okay, it doesn't match, so I copy the lower one. 12 matches in there. I increment, and 14 doesn't match. I'm finished actually. All right. What did you notice here? Did anything catch your attention? You didn't notice anything? Anything that was inefficient maybe, or? So you didn't find me repetitive at some point when I did that? Nobody in the room then?
Sorry? So jump a couple, 2 or 3 instead of just 1. I think that was the.
Yeah, exactly. That's probably this part that you mean, right? That we could optimize that.
Yes. Yeah.
Yeah, exactly. So you see, this is very inefficient. I kept repeating myself because we keep comparing and failing. And indeed, maybe we can do something about that. When can we actually encounter that? Well, precisely with the optimization I gave you, because if you start with the smaller posting lists and then you intersect with the larger ones, at some point, that's exactly what you're going to end up with. You're going to add with a very small one, that is your current posting list, and then the one of the longer ones that you prioritized at the end. So this is going to happen. So how can we solve that? And I think you gave the answer in the lecture hall. How can we do that? Indeed, by skipping 2 or 3 at a time. So the idea is this: to make it faster, imagine that I have this magical pointer that is in there, that just happens to be here, and that says, okay, by the way, you can directly go to 10 over there. So how can we use that pointer? Well, when I'm looking at here and here, by looking at here, I see it doesn't match, and I see I have a 10 in there. So I know that everything that is going to be in between here is irrelevant. It's going to compare to fail in comparison. So then it means, because I know it's sorted, I can use that pointer, follow it, and magically jump over there. And you see, I just directly jump, and then 10 and 10 and so on. Then I continue. This is called the skip pointer. It's actually very, very practical in order to solve this. And again, it's very relevant because of the optimization that I told you about with the order in which you do the merges. So in practice, this is what it looks like. Of course, it's not a magical thing. It's really just very created in a very orderly fashion. So we basically have a pointer, a pointer, a pointer. So basically a series of pointers on each posting list in that way. So here I jump to 4, I jump to 7, I jump to 10, and so on. And now, I don't know if, no, I have time actually. I can just ask you rapidly this question, and then I'll let you go. So this is my question. How big should the skip pointers be? Should they be maybe a length of 42 postings, the square root of the number of documents, the logarithm of the number of terms, the square roots of the length of the current postings list? So I'm asking about the how many you want to jump at the same time with the skip pointer. Aha. There is disagreements. Well, let me tell you, it's actually the square root of the length. So for example, if we have 16 postings, we just make it 4 times 4. That's the idea. Right. So that's what we do. Maybe I can show you. I still have 1 or 2 minutes before this is over. I think this is where we were. I think it's right there. Yeah, so in practice, we don't do this. This is too small, this is too big. What we do is the square root. 4 times 4, 5 times 5, 6 times 6. We just take the length, square root. Okay. So this is the skip pointer. All right. And phrase search, I'm leaving for next week. Well, we'll finish that, but now you know what a skip pointer is. And so I want to just now check that you have been following. So I need to reset it, of course, because that was nice. Okay, so before I let you go, please let me know if you understood what I've been telling you, if you were scared of all the challenges that I've shown you that there are for these languages. All right, that looks great. So now the ring is probably, the bell is probably ringing now, which is exactly the perfect timing. All right, so this is it for today. Thank you very much. Enjoy the exercise session. So you're going to be actually implementing things and the Boolean retrieval system. Thank you, Dan, for moderating this lecture. Thank you all for coming. And I will see you. So have a great weekend, and I will see you next week, as usual, at 2 for the continuation of this lecture. Thank you and goodbye.